I'm Veronica Zacek.
And I'm Heather Lee.
And we are doing the introduction to spectrophotometry, the absorbance spectrum of cobalt chloride.
The overview is basically the introduction, the experimental, results, discussion and conclusion, and also the references.
The main purpose of the experiment was to find the lambda max of cobalt chloride, create a standard curve using that, use Excel to evaluate the data that we had measured, and then calculate the concentration of two unknown solutions.
And basically every substance has what's known as the absorbance spectrum, and it's basically a substance can absorb certain wavelengths of light. And that happens by when an electron goes from a lower energy level to a higher energy level. And spectroscopy is the general form of spectrophotometer, and it's basically used to identify molecular properties such as bond length and also structure. And this can be done to find how much of a substance is actually present.
Spectrophotometry is used to determine the amount of light that passes through a substance, that is absorbed in a substance. The higher the concentration of the substance, the less the light that comes through. This relationship is also known as Bayer's law, where absorbance is equal to epsilon times concentration times kappa.
And basically, A stands for the absorbance, which is measured at a particular wavelength. And absorbance is directly correlated with %T, as %T is the initial light that gets through the sample. And the preferred choice of a wavelength can be found by seeing the substance that absorbs the most strongly, which is also known as the lambda max. And a standard curve can be constructed by measuring the absorbance of different concentrations at the lambda max.
For the experimental, what we did was we filled one cuvette, 3/4 full of 0.150 molar cobalt chloride to a solution. Then we filled a second cuvette full of deionized water, which we will refer to this one as the blank. From there, we zeroed out the spectrophotometer, and we put in the blank and calibrated it to 100%. And then the blank was replaced with the cobalt-2 chloride cuvette, and we should continue from there.
The percent transmittance and absorbance was measured using the spectrometric 20, and by pressing the mode button, we could find the absorbance and also the percent transmittance. And this was repeated for all wavelengths from intervals to 400 to 600 nanometers. And after every reading, the spectrometric 20 was zeroed out by using the blank.
Lambda max was then chosen and used to calibrate the spectrophotometer. From there, 8 test tubes were filled with different concentrations of cobalt chloride 2, and water. And each solution was then placed inside the spectrophotometer, and we measured percent transmittance and absorbance.
And 2 unknowns were given to us in a test tube by the professor, and using the same cuvette, it was rinsed out between to measure the %T and absorbance at the lambda max, which is 500 nanometers.
This is our results, table 1, the determination of lambda max. We used the spectrophotometer at different wavelengths, and the one with the highest absorbance was at 500 nanometers with an absorbance of 0.776, and absorbance does not have any units.
And this is an example of the absorbance calculation at 400 nanometers, and the %T at this wavelength was 84.0, and the absorbance, basically plug and chug 2 minus the log of 84.0, and then you get absorbance equals to 0.0757, and absorbance has no units.
This is our figure 1, the absorbance spectrum. You can tell from where it starts, and then it has an increase until it hits the lambda max, and then it begins to decrease.
And this is the construction of a standard curve, and this table shows the at lambda max, the different mixtures of COCl2 and deionized water, and we found the %T, absorbance, and concentration. The %T and absorbance have an inverse relationship to one another, and also concentration and absorbance have a linear relationship.
This is our results. The example molarity calculation, we use test tube number 3. We use the equation MCBC equals MDBD, and then we solved for MD. We plugged in our values and came up with that MD was equal to 0.0600 molar.
And this is the calculation for epsilon, and epsilon is absorbance over the concentration times path length. And basically you plug and chug the values from test tube number 3, and you found that it's 5.25 liters over moles times centimeters.
This is figure 2, our standard curve. The concentration, or the construction of the standard curve was the relationship between concentration and absorbance. And as you can see, as concentration increased, so did absorbance. And this is a linear relationship.
And this is the determination of the concentration of unknown solutions, and we had number 56 and number 57. And this is the percent transmittance and absorbance, and the percent T, as it increases, the absorbance decreases.
This is our calculation of the unknown concentrations. We have unknown 56 and unknown 57. We use the equation y equals mx plus b, which is also known as absorbance equals epsilon times path length times concentration plus b. We plugged in our values, and for unknown number 56, the concentration was 0.0641 molar, and then for unknown 57, the concentration was 0.0756 molar.
And for question 1, it was what is the relationship between percent transmittance and absorbance? And we found that there is a inverse relationship between that, and using table 1, you can see that at 400 nanometers, the transmittance was a little bit higher and the absorbance was very low at 0.0780. And then at 425 nanometers, the percent transmittance was 70.6, and it was a lot higher at 0.151 for the absorbance.
This is question 2. The data, in fact, did support our selection of lambda max. Our example is in table 1. It showed that at a wavelength of 500 nanometers, the value of absorbance was the largest with 0.776.
This is question 3, and we found that there is a linear relationship between concentration and absorbance. And basically, using table 2, you can see that because at test tube 1, the concentration was 0.000 molar, and the absorbance was 0.0140. And then for test tube 8, the concentration was a little bit higher at 0.150 molar, and then the absorbance was 0.778. And you can see Beer's law states that the concentration and absorbance are directly related to each other, and here's our unknown concentrations and absorbance.
For question number 4, we figured that the trends were as percent transmittance of a solution increased, the absorbance decreased, and also as the concentration of the solution increased, absorbance also increased.
And these are references of the lab book and also of the staff link. And these are our picture references. And thank you.
Thank you.